So like I said, what we need to do today is we need to go through basically error propagation, which is something we have to think about a lot more in analytical chemistry than we do in many other courses. So the first thing we're going to do is look at different types of errors, how you handle them through calculations, and then we'll talk about statistics. And I've got some example spreadsheets with stuff that you covered. One, you can go onto Canvas and download it, and that's what this is. It basically has the data that are in 3 of the problems we're going to look at later entered into the spreadsheet, so you don't have to do it yourselves. So it saves you a little bit of time. Okay, so we need to think about error a lot because, again, oftentimes when you're doing analytical chemistry, what you're doing is you're basically testing things to make sure that they comply with some specification, whether it be a manufacturer's specification, whether it be an FDA specification or something like that. And it's very important that you feel confident that your data is good. And so the idea of the statistics is it gives you some idea, how well does my data compare with other data that's out there? Or how much error is associated with my data? Those are things that we want to address here. So first of all, we can talk briefly about the different types of errors that are out there. First, every experiment that you do is going to have at least a small amount of systematic error associated with it. In other words, what errors come from the equipment or from the technique that you use? So what you can think about is if you weigh things on the balance is going to introduce a small amount of systematic error because most balances that are labeled as analytical balances are accurate to the nearest tenth of a milligram, 0.0001 grams. That's a systematic error. Okay, it's going to be there all the time. There's nothing you can do about it. And then you also have indeterminate errors or random errors that enter in from just human error. All right, for example, you do 3 titrations. It's very unlikely that you're going to get 3 titrations with exactly the same result, even though you use the same components for the titration, because of indeterminate errors. How you read a burette, how you read a pipette, those kinds of things. Now, of course, you want to minimize the random or indeterminate errors, but it's hard to do, okay, in some cases. If we were all perfect, we would have no random or indeterminate errors, but they do exist and they always will. Okay, so how do we deal with this? Well, first of all, we can define what's called absolute versus relative errors. I'm trying something new today and it's behaving strange, or it takes a little bit of time to get used to. Essentially, absolute error is to say, all right, I have a mass, and there's my absolute error, and there's a typo in here. This should be 1.0008 plus or minus 0.0001 grams. Okay, so absolute, oh, it is there. It just got moved over to the line. But absolute error is always set by the instruments usually, okay? In other words, you read a burette, you know you're going to read the volume to the nearest plus or minus 0.01 or 0.02 milliliters, depending on how the burette's calibrated. Same with the balance, okay? Those are absolute errors because they match the measurement. The units match the measurement. A relative error is one where you take the absolute error and you divide it by the value that you're measuring. So if we were to take the same measurement and calculate the relative error, what we would do is take the absolute error divided by the measurement that's made, and then sometimes we multiply by 100 or sometimes we multiply by 1,000 depending on the magnitude of the error. Okay, so in this particular case, if you were to do this, we would get 0.01% or 0.1 parts per thousand. That's a very small absolute error. Or if you can also report these absolute errors as just straight up fractions, in which case it would be 1 times 10 to the negative fourth. But oftentimes we use percentages or parts per thousand. And you'll see this in some of the labs that you do later in the semester. Okay. So here's what you want to think about. Why do we need both absolute and relative errors? Because if we're going to do calculations associated with numbers, what we want to do is we want to reflect the error in those calculations. So in the first case, if I'm going to add or subtract numbers with absolute errors, I'm going to use the absolute error. And essentially what I do is to get the error for my sum or my difference, I simply take the square root of the sum of each absolute error squared. So in this particular case, if I'm adding two masses together that both have absolute errors of 0.002 grams, to calculate the error that I'm going to report with my sum, I'm going to take 0.002, square it, add it to 0.002 squared, take the square root of the sum. That gives me this value, 0.002828, and I'm going to round that back to the appropriate number of decimal places. And so the result is, by adding these two numbers together, excuse me, the absolute error grows slightly. Okay, so you want to be comfortable with how you handle absolute error in the calculations that you do. And you'll see this on the first exam. On the other hand, if you do multiplication and division, what you're going to do instead is you're going to use the relative errors in the same formula. In other words, before I do my division here, what I'm going to do, in this particular case, I'm calculating a number of moles. Okay, I have a mass of a compound with a fairly large relative error, and I have a molar mass, and the molar mass is also going to have a small absolute error. Okay, you see some variation in molar masses that are reported on the periodic table. Okay, and so oftentimes you can say the absolute error is about 0.01 grams per mole, depending on isotopic measurements and all that. So in this particular case, what I'm going to do is I'm going to calculate the relative uncertainties, and so I find with my mass, the relative uncertainty is fairly large with respect to the molar mass. And so one of the things you can think about is if you run into a situation like that, probably the larger of the two absolute uncertainties is going to be dominant as far as your calculation is concerned. I'm going to plug those relative errors into the same formula, square root of the sum of the squares of the errors. And you see in this particular case, because the second relative error is so small, that the end result is the relative error that I'm seeing, it hasn't changed. But then what I have to do is I have to go back and change that relative error into absolute error in my final calculation. So this takes a little bit more working. And so this is what I would report. All right. So there you have the formulas that you need. Okay. You can calculate absolute error simply by dividing by the error by the measurement. Or you can do it in percent errors, or if you want to, parts per thousand. It doesn't really matter. They'll all work. Okay, so let's try a couple of examples. Everybody got their calculator? Get your calculators out. So this is more likely for analytical chemistry. We're taking a difference. In other words, we're trying to figure out the mass of something we've put into a container by subtracting the mass of the empty container. In this particular case, our absolute error is 2/10,000ths of a gram. So what are we going to report for our calculation? First thing we're going to do is we're going to take the difference between the two numbers. What do we get for that? Whoops. What's this? Okay, 7.062 grams. Ah, but wait a minute. That's what your calculator says. Is that the correct number of sig figs?
No, it should be one more.
Yeah. We're going to have to add a 0 there, right? Okay. So 7.0620 grams. Now, what's the absolute error for this one? To do that, we're going to take the square root of 0.0002 squared plus 0.0002 squared. And so if we do this, what do we get?
0.00028.
That's correct. So we're going to round this to 0.0003. And so what we would report for this difference is 7.0620 plus or minus 0.0003 grams. Okay, so that's the easy part. Now let's go on to the tougher part. Say we're going to calculate a density. So we've got a mass, we've got a volume. We can say, all right, this is a density calculation. What do we get for our density? .745. Okay, is that actually 3.745 is good because we've only got 4 sig figs on the bottom there. Or is it 3.746? Yeah, okay. So it rounds to 6. All right. Now, how do we calculate the error here? Probably the easiest way to do this is like this. You say, all right, I'm going to take the square root of 0.001 divided by 44.988 squared plus 0.01 divided by 12.01. And you're going to see, again, this is going to be the dominant of the two squared. And then what we're going to do is we're going to take that whole relative error and multiply it by my density, 3.746. Okay, that's accomplishing what I've done with the absolute errors in the previous slide all in one step. Or excuse me, with the relative errors. I don't know why I'm blocking on that today. It's bad. Relative errors are here because we're dividing them and then we multiply by the final calculation to get our absolute error. What do we get here? Okay. 0.008. Okay. Sounds good. And so that's what we would report for our density. Okay, we have the density measurement with the absolute error. Now, sometimes all you have to do is look at relative errors. You don't have to look at absolute errors. For example, the week after next, you're going to be doing a standardized solutions lab. You're going to be making solutions of sodium hydroxide and of hydrochloric acid. You're going to standardize those following well-established protocols. You're going to do it in triplicate, and then what you're going to do is you're going to calculate the parts per thousand deviation for each of your measurements with respect to the average. And that's going to be your indicator whether you need to do something again or not. Okay, it's already been established. Okay, a certain number of parts per thousand means you probably should do that trial again based on what other people have done previous. All right, so you've seen how to handle errors. You'll have a little practice on the upcoming homework. Let's talk about statistics. And that's really going to be the main focus of today. And then you'll get to practice some statistics on a spreadsheet as well. And I'll show you some of the things about the spreadsheets that you put together for the lab material on Monday. All right. So again, we have to say there is a certain amount of uncertainty in everything that we measure. Our measurements, because of systematic errors, there's going to be error, and because of random errors, there's going to be more error. And so we need a way of evaluating that data and saying, is it good? Is it reasonable? Or is there something wrong? Okay, now, if you're doing an established technique, this is really easy to do. You can compare your data to established data, no problems. If you're doing something new, then you have to talk about this in terms of repeatability. How well can I repeat my procedure to the point where I can see things going on? Grab a computer, John. Oh, he's got one? Okay, great, thanks. All right, so what we want to do is we want to lay some basic groundwork for statistics. And this is all stuff you did on Monday. Now you're going to understand a little bit more about it. First of all, if I collect a large set of data, the combination of systematic and random errors is very likely going to give me what's known as a Gaussian distribution. Okay, you get this classic curve, all right? The word that's used for curving grades, okay? When you curve grades, you assume there's a Gaussian distribution. And typically with large class sizes like they see over at Rutgers, this is an issue that comes up. Okay, you see these. Here we don't see Gaussian distributions, especially in really small classes. So, what kinds of things do we have to look at for this? If we have a distribution of any data, one of the what we can do is we can record each value, and we refer to each value as x sub I. Okay, so if I take a sum of those values, that means it's the sum of everything that's in there. Okay, n is the number of values. So this sigma represents sum. You've seen that before, I would imagine. So what are the statistical values that I'm going to look at? Well, first one, of course, is the average. Take the sum of all my values, divide it by the number of values. That's going to give me the average. If you go back to your Gaussian distribution, in a perfect world, the average would represent the peak of the Gaussian curve. Now again, that assumes a lot of data is being collected. If you collect only 3 data points, you're probably not going to see a Gaussian distribution. In fact, it's totally improbable. Okay. 2 other things that you see. If you look at a lot of drug studies or disease studies, okay, I've become very well versed in cancer statistics because of my sister and my parents. The median value is the middle value in the data, okay? And so this is kind of a strange thing. I'm not quite sure why they do this, but when you read about specific cancers, you always see them referred to as being the median survival rate. And so it's really not the mean survival rate, it's not the average survival rate, it's the middle value. Now, in a perfect world, I think the two would be the same, but they're not necessarily the same. There's going to be some difference between median and average. Okay. Sometimes you want to look for the mode as well. You want to look for the value. If you have a large set of data, is there a mode? Is there a value that occurs most frequently? As far as we're concerned, what's most important on this slide? Number one, the mean, and second, the deviation. Okay, so the deviation is defined as the difference between, or the absolute value of the difference between your mean and each value that you've collected. So if you have 5 data points, you're going to calculate 5 deviations for it. And this, again, is where spreadsheets really can come in handy. And I'll show you how to do this with a spreadsheet because it's really useful. So you calculate your mean, you calculate your deviation. All right. Relative deviation, then, is you take your absolute deviation, you divide it by the mean. Okay. And of course, you can also calculate the average deviation by summing up all the deviations you have and dividing by the number of data that you have. Okay, so if you report a deviation in parts per thousand, it's a relative deviation. That's what this would be. So in parts per thousand, you're going to say dr times 1,000. Okay, that's assuming your relative deviations are pretty small, which you can hope for. All right. Now let's look at some other statistical values. Those are just kind of the base values that you do. Here's a really important one. We report the standard deviation. Okay, now the standard deviation reflects how wide the Gaussian curve is based on your data. Okay, so what's illustrated over here is you have 2 Gaussian curves. One's much wider than the other. The standard deviation for the second Gaussian curve is much larger than the standard deviation for the first. The implication there is that the data for the larger curve is much broader. Okay, there's a much wider range of data. Does that mean they represent the same thing? That's a hard thing to decide. But you calculate a standard deviation by taking the square root of the sum of each individual deviation divided by n minus 1. And we often refer to n minus 1 as being degrees of freedom. That's how statisticians use that. So essentially what you can say is a standard deviation is the square root of the sum of deviations squared divided by degrees of freedom. Is the internet not working on that one? Yeah. So, how do you calculate a standard deviation? You can plug the formula in if you want to, or what else can you do? Most calculators, including the cheap scientific calculator that I recommend, have the ability to calculate a standard deviation, but you have computers. How are you going to do it? Yeah, spreadsheet. Whether it's Excel or something else, all spreadsheets have these basic statistical calculations built into them, and I'll show you how to access them as we go along. Okay. So now, let's talk about this idea of confidence intervals. This is a really tough one because there are a number of ways of representing this, and there are a number of different uses for it. When I first started teaching confidence intervals for the t-test, which is which this equation represents, I was essentially using the t-test as a way of representing absolute error for a given set of data. And that's one way that it can be used. In other words, I'll use the same illustration I used in lab the other day. Say, for example, we have two Gaussian curves. We have one here, and we have another like this. One of the ways we can use the t-test, and this is the way you're supposed to use it in lab, is you're supposed to say, all right, are these data, or can I be reasonably confident that these data represent the same thing, or are they something different? Okay, and so when you do the t-test, what happens is, for a specific set of data, you use the mean of that data, and you establish boundaries based on how much confidence, or how big your confidence interval is. If you have a 100% confidence interval, the boundaries are limitless. The boundaries get smaller as you lower the confidence interval. So typically what we do is we either use 90 or 95% confidence. I'd say for most measurements, unless you're told otherwise, use 95% confidence. And so one of the ways we could calculate this interval that I've marked out in green is using this equation. The average plus or minus t times the standard deviation divided by the square root of the number of measurements. Okay, now where do you get that t value? It comes from a table. So this is from another textbook, but your textbook has something very similar in it. So what we would say is, if, say for example, we have 6 data, and we want to calculate, or we want to figure out what the t value is for 95% confidence, our data is going to have 5 degrees of freedom. And so therefore, the value of t we would use is 2.45. Okay, so that's one way of doing this. The other way, sorry?
I couldn't get it because you said it was going to be 5 degrees of freedom, and then you used the number selected was only 6 degrees of freedom.
Was it?
Yeah.
Yeah, maybe so. You're right, 2.57. Okay, yeah, so you're right, this is 6 degrees of freedom. And actually, you'll see this in a little bit because I've got a bunch of, or some data that has 6 degrees of freedom. So that's one way of doing it. So essentially what you could do using that method is say, okay, I can calculate my absolute error using the t-test. More commonly is this way. Say, for example, you're analyzing a pharmaceutical compound. Okay, you work for a company that makes ibuprofen. All right. As part of the quality assurance for any sample of pharmaceuticals that goes out, what you have to do is you have to prove the purity of the sample that you have, okay? And so there's already established data. Okay, so say for example, you're testing 200 milligram tablets of ibuprofen for the correct dosage. All right, you come up with 202 milligrams as your average once all your tests are done. Is your average statistically the same, or is it not the same as what company has read for all of its other samples? That's what this equation is. The mu value is the accepted value, okay? Or in the case of the lab, what you're going to do is you're going to compare 2 different values using this same idea. So you take the absolute value of the difference times the square root of the number of data divided by S. And then you compare that to the average, or to the tabulated t value from the table. Okay, so in this particular case, if I calculated for 5 degrees of freedom, if I use this equation to calculate the t-value for that, and I got a t-value of 3.00, that's greater than the tabulated value, which we read as 2.57. And so we can say we're reasonably confident that these data are not represented, or they're not the same. So in other words, what the company would conclude from this is probably they've got a bad batch. On the other hand, if I calculated a t of 1.69, then that's less than this 2.57, and that's telling me that these two data match each other. Okay, you can, with reasonable confidence, you can say they're the same and they represent the same thing.
What if it was 2.56?
Still less than that 2.57, so it's still in that 95% confidence interval, but just barely. If you went to 90%, it would be out. That's the thing you want to think about. And depending on how ethical a pharmaceutical company is, they probably chuck a piece of data or a sample out like that. Okay, this is one of the problems that we're seeing right now, is the regulation of pharmaceutical companies is not at least what it should be. And there are a lot of pharmaceutical companies that aren't doing the analysis data to FDA standards. It's one of the problems with generic pharmaceuticals to begin with, okay, is that they don't always, or the generic pharmaceutical companies are not scrutinized in the same way as a company that first produces a compound, and oftentimes as a result, they don't do the testing. And then if the FDA comes in later and checks things out and finds this, then the company gets fined a huge amount of money. If you go on the FDA website, you can see lots of examples of these kinds of things where companies are not testing their products adequately. Okay, so here's one of the things, or what I recommend you do. If you go into Canvas, under this week, you can, I put a link to a file up on Canvas that you can download. And what it does, or what it has, is it's got 3 spreadsheets in it with 3 different problems. Okay, and this is the first of the problems. And so here's what we've got. We're calculating the percentages of a certain compound using a new analytical method. We know from previous data that we should get exactly 100% for this. And so what we want to say is we want to use the t-test to calculate, are we within that confidence interval? Okay, alpha equals 0.05 means we're talking about 95% confidence for this. So what we need to do is we need to calculate the t-value, or excuse me, we need to calculate, the t-value for this relative to the other data. How are we going to do it? Let's go to the spreadsheet and take a look. So this is the first problem here. Now here's the question. I've got 7 data points. What do I need to do to calculate a t-value? Yes. Okay, so how am I going to calculate the mean? Okay, that's the hard way. What's the easy way?
Equals average.
Yes. So we can go into Excel. This thing will connect. There we go. And we can take equals average. And usually when you start to type this, Excel will pick up the particular function that you want to. You can. Why is this thing misbehaving? Anyway, I can just type it all the way out. Open parentheses. And then what I can do is I can just select through my data. So I go like this. I can just drag through there, and you see how it's selected the contents of A2 through A8, and then close my parentheses. Hit enter. There's my average. Now what if I want to calculate a standard deviation? Don't I need to do that as well? Very easy in Excel. Equals STDEV. Open parentheses, and then I can select the same data. So that's a pretty large standard deviation, and that's going to affect how I calculate t-values. All right, so let's go back and look and see what else we need to do this. I've got my mu value, I've got my n value, and I've got my s value. Okay, so I know my mu value in this problem is 100% even. Okay, it should be exactly 100%. I'm a little ways off from that. Oops, come on. So, in this particular case, t is going to be equal to the square root. I've already forgotten the formula. Oh, yeah, it's the absolute value of the difference between the two times the square root of n. So in this particular case, we have 7 values. So we're going to say it's the absolute value of 100 minus our average, which I've already forgotten, 99.257. That's probably way too precise. Times the square root of 7 divided by a standard deviation. .35, we'll do 2.346. That should be plenty. So what do we get for a t-value? Well, that's what those straight brackets mean absolute value. So if you get a negative number, just drop the negative sign.
I got 69.3.
69.3?
Yeah, well, that's my calculation is weird.
But the bottom number is 2.346?
Yeah, 2.346.
I got 0.837.
Yeah, that sounds better.
0.38.
0.387?
Yeah, 0.838.
Oh, 838.
Rounding up.
Okay. All right. So, can we be confident that this data is similar to the accepted value? How are we going to tell? We're going to have to go back here, look at this table. If we have 7 data, as we do, that means we're going to have 6 degrees of freedom. So we're going to look here. For 95% confidence, the t-value is 2.45. And so what we would conclude then is here, this is significantly less than that 2.45 value for 95% confidence, and so that means our data are probably the same. If that value or the absolute value of that value, because that's one of the things you'll notice with your spreadsheets is when you plug in everything to the t-test function that's part of Excel, it doesn't take the absolute value. Okay, it's doing effectively the same calculation as we've done here with your data. It's designed to do it with large sets of data. That's one of the reasons it's there. I mean, you could actually do 10 data by hand pretty easily, but it's a lot easier just to set it up in Excel to do it. Okay, so these two things are, what this is saying is even though we've got a fair spread of data, this is likely the same. Now here's a question. What do you notice about this data? It's in percentages, but look more carefully at it. Is there a serious outlier here? Yeah, the 103 is a significant outlier. And so one of the other things that you have to evaluate is you look at this data. Okay, we're evaluating. There's quite a bit of variance here. And one of the ways you see that is if you look at the standard deviation, it's pretty large. If we were to cut out the outlier, our standard deviation would go down. It would mean our data is much tighter. That would actually increase the value of t because the standard deviation is on the bottom here. It would tighten our data up though, and it would look a lot nicer. How do we evaluate whether we keep some data or not? What do we do? That's what we have to think about next. Actually, there are two things we have to think about. First of all, we have the F-test. And essentially, what the F-test is doing is saying, okay, if you have two sets of data, are the standard deviations significantly different or are they the same? And so you take the standard deviation for one set of data, square it, you divide that by the square of the standard deviation for a second set of data, where you put the larger value on the top. Okay, so F is always going to be greater than 1. And then what you do is you go and look on this table and decide, based on the number of degrees of freedom for both your sets of data, if my F value is greater than what I see here, they're significantly different. If it's less, then they're pretty much the same. Okay. If an ideal would be an F value of 1, where you have exactly the same standard deviation for both sets of data. That's one thing to evaluate. This is another. How do we decide if data is an outlier or not? Okay, and that's what the Q test is. You were asking me about this on Monday. It's a very simple test. Q is defined as gap divided by range. And then once you get that Q value, you compare it with tabulated Q values depending on the number of degrees of, or excuse me, the number of data that you've collected, not degrees of freedom. Okay, so note the difference here. This is N, not degrees of freedom. So let's go back. Actually, let's go back to our data on the spreadsheet. That's easier. How do I evaluate Q for this data? Should I throw out that 103? Now, one of the easiest things to do, first of all, is to select your data and sort it. So we'll sort smallest to largest. Okay. Now, what's my range? Range for that data is 103. 103.93 minus, I've already forgotten what it is, 96.7. Okay. And the gap is 103.93 minus 99.84. That's pretty big. What's that?
4.09.
So in this particular case, my Q would be 4.09 divided by 7.23. Okay. So let's go look at this table again. I have 7 data points. So it's actually it's based on n, so I'm going to look at 7. Ooh, I'm really close, but I'm not quite there. So according to this, within the 95% confidence interval, even though that one piece of data is significantly different than the others, it's not quite different enough that we can eliminate it by the Q test. All right. Now, here's another thing. It's kind of strange. There's a second test that you can do called the Grubbs test. Again, what you can do is you can say, all right, I've got a questionable value. I can take the absolute value of the difference between that and the mean and divide that by the standard deviation. So in the case of our data, let's look at that. We have 103.93. Our average is 99.26. Our standard deviation is 2.35. We'll use 2.35. Okay, so here our Grubbs factor would be the absolute value of 103.93 minus, what was it, 99.26 for the average?
Yeah, 99.26.
99.26. And then we're going to divide that by the standard deviation, which was 2.34. 3.6? Okay. So what's my Grubbs factor? Okay, and so we can compare that to tabulated values. We have number of observations, 7. The Grubbs factor in the 95% confidence interval is 1.94. So by the Grubbs test, we could eliminate that data. By the Q test, we can't in 95%. So there is a slight difference. So here's a question, and I've not been able to answer this question. Which one do you use? And when do you use each? The answer, I think, has to do with data set size. Notice how, for the Grubbs test, we have much larger numbers of data. Okay, and the interesting thing about the Grubbs factor, too, is it goes up with the value of data, whereas the Q factor goes down as you increase the number of data. My guess, I need to find a definitive answer for this, is that the Grubbs test is used for larger sets of data than the Q test. But what you should do is if you're asked to do one of these tests in a lab, just follow it, okay? Because in many cases, the labs were written by Dr. Yarmchuk, who has a good background in statistics. Okay, so think about that. Sometimes you do the Grubbs test, sometimes you do the Q test to decide whether data should be thrown out or not. Okay, and that's the question I asked here. How do you know which to use? All right, let's talk about how you use Excel to do some of these things. Okay, over here I have a set of data. Once I calculate the mean for the data, I can calculate the deviation, and that's what this is showing. Okay, the deviation is the absolute value of the difference between the data point itself and the mean value. Okay, now why do I put dollar signs in front of the cell reference for the mean? What does that do?
We change the format?
Nope, doesn't change the format. Here's what happens. I can type this function into this top cell here, okay? The way I have it there. If I copy the function down, this value, A2, will change to A3 for the next row down, and A4 for the next row, and next row, and next row, okay? If I left the dollar signs out from the reference for the mean, it would also change the value of this cell reference. So what we call those dollar signs is they're absolute references. In other words, if you copy the function, those don't change. If you leave those out, the cell references do change. And then what it allows you to do is to copy a function down a whole bunch of data. Okay, so I have the mean in one spot. I want to keep it there. Even if I do copy the function down, I'm going to use those dollar signs. Next thing, I want to calculate parts per thousand. Again, I'm going to calculate the deviation, and then I'm going to multiply it by 1,000. Or actually, I'm going to divide it by, first of all, divide it by the average, and then multiply by 1,000. So I'm going to take the deviation divided by the average, multiplied by 1,000, and these are the parts per thousand that I get. And of course, to get the standard deviation, you do that. Get the average, you do that. We've talked about, or we showed that earlier. So there are your references. Now, one other thing you want to be mindful about in Excel is that Excel does not handle significant figures. You have to force it to handle significant figures. Now, here's the question you want to ask yourselves philosophically. Is it worth the bother? It depends. It depends on what you're using the spreadsheet for. If you're going to be showing data using a spreadsheet, then yes, you do want to mess with sig figs. If you're using the spreadsheet to calculate things that you're later going to go on and do something else with, then you probably don't have to worry about sig figs so much. Okay, for example, I was careless about the number of sig figs with these parts per thousand because the deviation only has one sig fig, therefore the parts per thousands also should have only one significant figure. All right, so what I set up is a couple of problems that we can practice with. And this is the first one. We've got a set of 8 data. We want to calculate the average deviation and the standard deviation for the data, okay? And then we want to use the Grubbs test to decide if we are going to throw out any data on this. And so if you go to the spreadsheet that I recommended you download, the second set of data, labeled Grubbs, if I can get to it, come on. There we go. It's a little funky the way it copied, but it works. Okay, so here's what I'm going to do. I'm going to start out, number one, by sorting this data. So I'll go down, I'll select all my data, I'll go to sort and filter, and I'll sort smallest to largest. Okay, that way I can see that. You don't have to do this. It just makes it easier to find what outliers there are. All right, in this next column, I'm just going to put a title on each of these columns. I'm going to put parts per thousand, or excuse me, I'm going to put deviation. Come on. And then the next column over, I'm going to put parts per thousand. And then over here, I'm going to type, all right, what's the mean? Below it, what's the standard deviation? Okay, so let's start by calculating the mean because we need that for parts or for the deviation. So we go equals average open parentheses, and again, the easiest way to do this is just to start at your data and select through the data that you want to take the average of. Just goes in there automatically. Then I can close parentheses. There's my average. Okay, let's do the same with standard deviation. Equals okay, so there's my average and my standard deviation. Now, how do I calculate deviation?
Deviation was the average.
Yeah. So I'm going to go over here. I don't know why this is behaving a little strange. Let's see if I can get out of this.